Hello everyone. So, welcome back to the next session of this P block elements 2. Yeah, as I said previously, we are not going to deal with this unit completely as a great period of 45 minutes or 1 hour or more than 1 hour, something like that. Instead, we shall go for a small time or a very short time, so that we can easily wind up this unit just like that. You can just, as I said previously in the video of the same unit in part 3, while traveling itself you can have a glance at it. So, in such a way you can able to wind up this unit so quickly, and this is the big unit in the very first volume of our metric chemistry textbook. Yeah. So, we shall proceed with this, the part 4. So, in the previous classes what we have dealt is, we have dealt completely with this group 15. Now, we are entering to the group 16, which is an oxygen family, which is also called as chalcogens, which means all the members of the oxygen family are called as chalcogens. That is what. Then specifically with this oxygen, it is the most abundant element that we have come to know. Yes, among the group itself, this is the most abundant element, no doubt in that. Then this oxygen exists as an oxide as well as molecular oxygen. That is what it is mentioned as a dioxygen. In air it is present as a dioxygen. If you compare the mass in terms of a percentage or the weight in terms of a percentage of the whole air, oxygen occupies the 20 percentage, not only 20 percentage by mass as also as volume. So, both it occupies nearly 20 percentage over here. In earth crust, it occupies 46.6 percentage of an O2 and 0.034 percentage of sulfur. That sulfur exists as a polyatomic S8. So, these percentages are given in terms of a weight, right. So, obviously, most of the rocks contains carbonate. If it has a carbonate, it must have an oxygen in it. So, it directly means in such a way. Then the sulfur is also exists in the form of a sulfates and sulfide. The prime ore for the sulfate can be said as a gypsum and epsom, in which sulfur is very prominently present. Sulfide, galena and zinc blende, ZNS and PBS, which is widely known from the first unit itself. Rest of the element, if you see other from oxygen and the sulfur, selenium, tellurium and polonium, etc., these elements are actually found very little amount. That is what here it is mentioned as a scarce. So, very little amount, and they are exist as an selenites, tellurites, which we will be able to get not isolatedly, but when we are extracting the sulfide ore, along with that we will be able to get this tellurium and selenium in the form of selenites and tellurites. Then the next one, physical properties. See, at 293 Kelvin here, this oxygen actually exists as a gas, and the sulfur, selenium, tellurium and polonium exist as a solid. See, these are the data which is given as a tabulation in our textbook, collecting all those data, and I am giving it very precisely over here. So, at 293 Kelvin here oxygen exists as a gas, rest of the elements like sulfur, selenium and tellurium and polonium exist as a solid. And all these elements, if you look at it down a group, atomic number, mass number, atomic radii, density increases from oxygen to polonium, which means down a group all these 4 properties will definitely increase. Z corresponds to atomic number, A corresponds to mass number and atomic radii and density, right. The next one, melting point and boiling point. See, melting point of oxygen is around 554 Kelvin, something like that, but the oxygen for sulfur it is around 350 to 400. Okay. See, let us see first. So, this melting point and boiling point actually increases from oxygen to tellurium, and further it decreases to polonium, which means from oxygen to tellurium will definitely increase, from tellurium to polonium will definitely decrease. That is what here it means. And to be discussed with the next point, see, you will be able, as I mentioned, the melting point of an oxygen is around 54 Kelvin, but if you look at the melting point of the sulfur, which is around 350 to 400 Kelvin, there is a drastic increase in the melting point when you move down a group. the drastic increase in melting point is because of the existence of oxygen as a diatomic and sulfur as a polyatomic, I would say octatomic also, right. So, that is the reason you are able to find a large difference in the melting point and boiling point over here, right. Then here it is mentioned from tellurium to polonium it decreases. Why it decreases? Because of inert pair effect. Inert pair effect in the sense it is the reluctance of an NS electrons to take part in bonding and remain inert. They will not be taking part in the bonding, which means they do not have a capability to excite. So, that is the reason here from tellurium to and polonium the melting point and the boiling point decreases. So, that is it with the physical properties. So, 293 Kelvin, oxygen only exists as a gas, rest of the element exists as a solid, atomic number, mass number, atomic radii density increases from oxygen to polonium, no doubt in that. This melting point and boiling point increases from oxygen to tellurium and decreases to the polonium. There is a sudden increase in the melting point and the boiling point from sulfur, from oxygen to the sulfur. It is all because of their existence as a diatomic and the octatomic. Then the polonium decrease in the melting point and the boiling point from tellurium to the polonium is completely because of the inert pair effect, which I have mentioned as it is a reluctance of an NS electron over here. The next one, oxygen, its preparation. See, in atmosphere actually it exists in the percentage of 23% in atmosphere. Then in water it exists as a 83%. We know that H2O obviously by percentage with the mass itself, oxygen will occupy the very first position followed by the hydrogen in the water. How it has been prepared? Industrially it has been prepared by the fractional distillation of a liquid air. Fractional distillation is a method where liquid air will be vaporized with the help of a condenser. What happens there? Oxygen alone will start to get vapor at a particular temperature. Those vapors are collected and get condensed with the condenser, water condenser. So, we will be getting as an oxygen there itself. So, that is the thing. Then in laboratory how it has been prepared? It has been prepared by the decomposition of hydrogen peroxide with the help of manganese dioxide, very first method, which means hydrogen peroxide H2O2 will be decomposed to give H2O and O2. This is the very first method and this will be catalyzed by manganese dioxide. So, this is the first method of preparation of this oxygen in the laboratory. Then the second method of preparation over here is we can able to oxidize this hydrogen peroxide with the help of an acidified potassium permanganate, which means the hydrogen peroxide will be taken to that potassium permanganate. I am just taking in the form of an ion, to which acid, which means the reaction is taking place in the presence of an acid. In the presence of an acid, Mn plus 7 oxidation state will be changes to plus 2 oxidation state. So, therefore, here it is Mn2 plus and our product is molecular oxygen over here. So, that is it with this, right. Then, so this is the very two best method and the given method for the preparation of this oxygen in our textbook. The next one, the third method of the preparation is just by the decomposition method, which means if I take the mercuric oxide HgO, this mercuric oxide will be heated to give mercury and molecular oxygen. So, 2 moles over here. Then barium peroxide BaO2, this will give barium oxide and molecular oxygen. So, if I make it as 2 over here, balanced. Then potassium chloride, it is a famous decomposition reaction, KClO3, KCl plus O2. So, to balance with 2 here, 2 here, 3 here. So, that is it. Then potassium nitrate, KNO3, it forms potassium nitride, KNO2, by evolving the molecular oxygen over here. So, to balance with 2 here, 2 here, that is it with this. So, these are all the very best decomposition and the easiest decomposition through which we will be able to prepare this molecular oxygen here. The next one, physical properties. It does not have any color, it does not have any smell, it does not have any taste, very first. The next one, it exists as a diatomic gas, it is very clear, and triatomic when it exists in the form of an ozone. and these are completely paramagnetic. When I specify something as a paramagnetic, which mean it has unpaired electron in it. The very important thing over here is it has unpaired electron in it. You will be able to understand this if you know this molecular orbital theory. You would have studied in the class 11 itself, right. So, this paramagnetic tells us it has an unpaired electron, so it will be definitely getting attracted to a strong poles of a magnet. Then oxygen is more electronegative. When it approaches hydrogen, since oxygen also has lone pair of electron in it, it will definitely form an hydrogen bonds over here. Then how it has been prepared, which means the ozone. The liquefied this liquefied oxygen, what will be done is, will undergo a process called fractional distillation to give a purest form of an ozone. The color of the purest form of an ozone will definitely be pale blue, no doubt in that. So, this liquefied ozonized oxygen will be fractionally distillated to give pure form of an ozone, where the color of the ozone over there, which is in the pure form, will be pale blue in color. Then how does ozone is formed in the upper atmosphere? It is because of a kind of a fission taking place in an oxygen with the help of an UV light. So, in the upper atmosphere, the oxygen, molecular oxygen has been broken. So, we will be getting an atomic oxygen. That atomic oxygen will trigger one more molecular oxygen, thereby we will be getting the ozone. This happens above the sea level over here. Next one. How it has been prepared in the laboratory? This molecular oxygen will be subjected to an electric discharge, which will generate 20,000 volt. This 20,000 volt of this electric discharge does some reaction. What is that reaction? See, as I said, the molecular oxygen with the help of an UV light or with the help of an electric discharge will be getting as an atomic oxygen. This atomic oxygen is unstable. This will obviously trigger the other molecular oxygen to form ozone. So, this happens over here. Wherever the ozone forms, this happens, right. Here, out of all the oxygen which we have, if we assume that we have 100% of an oxygen, if you do this process, only 10% of an oxygen will be converted into ozone. See, this is an experimental data. From various experiments, it was found only 10% of our oxygen will be converted into ozone. So, ozonized oxygen. So, that is what here it means. Then structure of this ozone. The structure of this ozone, it exists as a bent shape, which means oxygen, oxygen and oxygen. I hope you are aware of this Lewis dot structure. You have to count the valence electron of this oxygen. So, 18 altogether, 2 bond, 4 electron have gone. We have got 14 electron. If you distribute this 14 electron, there is one chances where you will be getting a double bond over here and a single bond over here. Okay. The single bond over here will be taking the charge minus charge. Either of the oxygen will have a negative charge. It can be any oxygen, OA or OB, something like that. Then this electrons are, this structure is actually symmetrical, where the pi bond are completely delocalized. As I have mentioned, if this bond shift here, this will definitely exist as O minus, and oxygen over here will form a double bond O over here. So, this happens. So, that is the overall structure of this ozone. Next one, chemical properties. See, all the active metals, which mean the very first group 1 element, will react with an oxygen even at the room temperature itself and forms an oxide, sodium oxide, potassium oxide, etc. Then there are some less reactive metals which belongs to the transition metal like iron, aluminum. These will undergo a process called oxidation very slowly. That is why rusting of iron takes place a bit slow. See, when these less reactive metals like iron and aluminum, when it is treated with the molecular oxygen, it forms an oxides of a metal, and during this reaction exothermic, which means heat will be liberated, no doubt in that, because they are very less reactive. So, in order for the reaction to occur, it must take a lot amount of energy. When the reaction occur, it will liberate certain amount of energy. So, that comes as an exothermic, which the heat have been liberated. These types of metals, which mean the metal which is finely powdered, is considered as a pyrophoric. Why it is called pyrophoric? Which actually after powderizing it, when it is set on fire, large amount of heat energy will be liberated. Only those metals are actually called as pyrophoric. Don't forget it. Not all the metals are pyrophoric. When those metals are pyrophoric, because when after grinding it and taking into a powder, when it is set on a fire, heat should be liberated. So that's the thing. Next one. Oxidizing nature of this ozone. See, this ozone is capable of oxidizing this potassium iodide to just iodine. How it does? See, this ozone, the molecular formula is O3 plus the potassium iodide Ki, then H2O. It forms potassium hydroxide KOH, then molecular oxygen, then iodine. This is the overall reaction which actually takes place. Balancing is quite known for you people, you can do it, no need not to worry. Here, what is the thing that we need to check out over here is, the oxidation state of this iodine over here is -1, here it is 0. So, what happens? Nuclear charge increases. When the nuclear charge increases, it means oxidation, which means the ozone which is present here act as an oxidizing agent. When something is an oxidizing agent, it will not undergo oxidation. Instead, it will oxidize the other substance which is reacting with itself. So, here ozone is an oxidizing agent. The one which is reacting with the ozone is potassium iodide. In potassium iodide, iodine have been oxidized. So, that is the reason. Right. So, in order to estimate how much of ozone is present in a particular amount of a substance, quantitatively, we can use this method. Then, next one. Uses. In order for a human to live, not for the human, even for the animals and living organisms, I would say it is a very, very important one. Then in oxyacetylene welding, it is a very definite component. Then fuel in rockets, it has been widely used over there. So, this is an use of an oxygen. Then use of an ozone, if you look at this ozone has a good oxidizing nature, as we have seen just now. It is a good oxidizing agent. So, it can oxidize even the organic compound itself. 1. In acidic medium, the oxidizing power of the ozone will definitely exceeds the oxidizing nature of this fluorine and as well as oxygen over here. In acidic medium, I said. So, if we need something like more powerful oxidizing agent than fluorine and oxygen, we can take ozone in acidic medium. So, the definitely oxidizing power will be enhanced. In alkaline medium, what happens? This decomposition of ozone takes place very slowly. Once it decomposes, it starts oxidize the other substances. In alkaline medium, here the decomposition is suppressed. That is why in alkaline medium, ozone as an oxidizing agent is not at all preferable. Next one. Right. Allotropic forms of a sulfur. Quite easy to learn. Sulfur actually exists in two forms, crystalline and amorphous. Crystalline, it exists as a rhombic and monoclinic, which is said as alpha sulfur and beta sulfur. Amorphous, it exists as a plastic sulfur, milk of sulfur, then colloidal sulfur. This plastic sulfur is actually called as a gamma sulfur. That is what. So, we can categorize this sulfur into two different forms, and among those two, we have certain amount of classification like rhombic and sulfur, monoclinic sulfur comes under crystalline. In amorphous, we have 3 plastic, milk of sulfur, then colloidal sulfur. First look at one. See, rhombic sulfur, which is called as actually alpha sulfur. Among all the sulfur, this is the most stable sulfur at room temperature and the pressure thermodynamically, I would say. So, that is why it is mentioned as thermodynamically most stable form at the room temperature and pressure. This sulfur actually exists in the form of an S8. S8 in the sense crown like a structure. It is very well known to you all. Sulfur will exist as a crown like a structure. S8. So, this is called S8, which exists as a crown shaped structure. That is why it is mentioned as a puckered ring over here. This sulfur actually exists in an yellow color, and it is insoluble in the water and soluble in organic solvents like carbon disulfide. So, that is it with the content of this rhombic sulfur. See, most stable form at the room temperature and the pressure, exists as the form of an S8 in the crown shape, which is called as a puckered ring, then yellow in color, which is insoluble in water and the soluble in carbon disulfide. Then next one. This rhombic sulfur can be converted into monoclinic sulfur. I would say this is the preparation of the monoclinic sulfur itself, because how will you prepare monoclinic sulfur from the rhombic sulfur? You see, I need to heat this rhombic sulfur slowly at 96 degrees Celsius. So, if I heat it slowly, definitely at 96 degrees Celsius, you will be able to get monoclinic sulfur. How do you do the reverse one? See, the monoclinic sulfur can be converted into rhombic sulfur if you cool it below 96 degree. So, above 96 degrees Celsius, rhombic will be converted into monoclinic. Below 96 degrees Celsius, monoclinic will be converted into rhombic. So, that is what. See, here the monoclinic preparation is already given here, need not to do it again over here. There in rhombic sulfur, sulfur exists in the form of an S8, which is set as a puckered ring. I said it as a crown. Here, in the monoclinic sulfur, sulfur exists in two different forms, which mean S8 and S6. S6 will be existing in the small amount along with the S8 itself. And this monoclinic sulfur, which is actually existing in the form of a needle-like prism, that is why it is mentioned as a prismatic form over here. There it is, I said this rhombic sulfur, as it is thermodynamically more stable at the room temperature and pressure. Here the stability exists between 96 degrees Celsius to 116 degrees Celsius, because above 96 degrees Celsius only rhombic sulfur will be converted into monoclinic sulfur. So, below 96 the existence of the monoclinic sulfur is just impossible. So, that is what here it means. So, they are more stable at the 96 degrees Celsius and 116 degrees Celsius. Then next one. This if you need to prepare a plastic sulfur, what you need to do? You have to take the sulfur, you have to heat it, you have to bring it in the molten form, and you have to pour that molten form of the sulfur which you have heated to the cold water. Once you do that, you will be getting a yellow rubbery ribbon which is called a plastic sulfur. You will definitely get no doubt in that. Since it is yellow rubbery ribbon which is plastic sulfur, it will be very soft, it is rubbery and it can be stretched so easily. So, how do we get this rhombic sulfur back from the plastic sulfur? By cooling it slowly. Once we know that plastic sulfur is a yellow rubbery ribbon, it will be very rubbery, stretched easily and very soft. On cooling down, definitely it becomes hard. So, it will definitely turns into a rhombic sulfur, where this rhombic sulfur is quite stable. So, this is regarding this allotropic form. Then this sulfur is also exists as a liquid and gas, which we have seen previously are solids. Here this sulfur is also exists in the form of a liquid as well as gaseous state. So, in the form of a liquid, how it exists? You have to take this monoclinic sulfur. If you heat it above 160 degrees Celsius, it melts. The form of the sulfur will be changed into a lambda form, which is lambda sulfur, which will be a yellow liquid. Yellow liquid in the sense it will definitely move, so it must be a mobile pale yellow liquid. So, this is with respect to the sulfur in the liquid form. In the vapor form, 90% of the sulfur will exist as S8, S6, S7, S6, and even in the small amount we will be getting S2, S3, S4 and S5. 90% overall in the liquid form, in the gaseous form, I would say 90% will exist as 8, 7, 6 and so. Then S2, S3, S4, S5, these are all exist very small amount along with that 90% of S8, S7, S6. So, this is what it means, which I said in vapor phase. Which one I have discussed, the lambda sulfur is a gaseous phase. The previously which we have discussed, rhombic and the monoclinic sulfur are in the solid phase. So, that is it with this regarding the allotropic forms of a sulfur. So, in this class what we have discussed over here is, we have come across oxygen, its preparation, ozone, its preparation, the properties of an oxygen, to prove that ozone is a good oxidizing agent with the help of a potassium iodide to iodine, then followed by the uses of those oxygen as well as ozone. Then we have begun with the allotropic forms of a sulfur. So, that is it with today's class. We shall go with the chlorine and the group 17, group 18, etc. in the following sessions. So, give a thumbs up, kindly share this video to your friends. So, see you all in the next class. Thank you.